Hey, what's up everyone? In this video, we are going to solve a very easy to understand problem that is available on Leetcode. The simplicity of this problem makes it a very good candidate for anybody who wants to learn dynamic programming and is just getting started. And because it is a beginner friendly problem, I have chosen this as a first problem in our dynamic programming series. Hey, Bhavesh here, and on this channel we learn and apply various data structures, algorithms to solve interesting programming questions. So if this is your first time on this channel, consider subscribing. So let's take a look at the problem statement first. You are climbing a staircase and it has n steps. You want to reach from the bottom to the top, and every time you can make 1 or 2 steps. We want to find how many distinct ways are there to reach the top from the bottom. We will see a few examples and that should make this problem even clearer. So let's say this is the staircase. You are at step number 0 and you want to reach the step number 1. So how many ways are there to reach from 0th step to first step using only 1 or 2 steps at a time? The answer is fairly straightforward. There is just one way of reaching from 0 to 1, and that is by taking 1 step. If you take 2 steps, you directly reach 2. You are never going to be able to reach the step 1. So there is only one way of reaching from 0 to 1. We can make a note of this. So for reaching the step number 1, there is only one way. Now let's say we want to reach the step number 2. As we are allowed to take 1 or 2 steps at a time, if we take directly 2 steps, we are going to reach the step number 2, and hence this certainly counts as one way of reaching the 2 from 0. Is there any other way? Of course there is. You can go from 0 to 1, which is 1 step away, and from there we can again take one more step to reach 2. So all in all, there are only 2 ways of reaching 2 from 0, and those are either take directly 2 steps at a time or take 1 step from 0 and reach the step number 1 and take one more step from 1 to reach the step number 2. You can note it down. For reaching 2, there are 2 ways. Now let's say we want to reach from 0th step to the 3rd step. This time we cannot take directly 3 steps because we are only allowed to take 1 or 2 steps at a time. So if we begin with 2 steps, we are going to reach the 2nd step, and then there is only one way we can reach the 3rd step, that is by taking 1 step. Hence, taking 2 steps at a time and then taking 1 step at a time is a certain way of reaching the 3rd step. What else can we do? From 0, we can of course go to the 1st step by taking 1 step at a time. How can we reach 3 from 1? We are allowed to take 2 steps at a time. So from 1st step, we can take 2 steps at a time and directly reach the 3rd step. And hence taking 1 step to begin with and then taking 2 steps is another way of reaching the 3rd step. From 0th step, we went to 1st step by taking 1 step at a time. From 1, we directly took 2 steps, but we also had the option to take only 1 step. In that case, we would have reached the 2nd step by taking 1 step. Now from 2, we need to reach the 3, and of course there is only one way, that is by taking 1 step at a time. Hence, to reach 3, we can also take 1 step each time, and that way we can reach the 3rd step. So we can note that for reaching the 3rd step, there are 3 ways. While we are at it, let's also take a look at reaching the 4th step from the 0th step. In all these ways that we discussed, we try to go from 0th step to the nth step. But on the other hand, we can also think of it in the opposite direction. So for example, we can say that to reach the step number 4, it is unavoidable to reach either the step number 3 or the step number 4. Without reaching at least one of these 2 steps, we cannot reach the step number 4. So now let's put it this way. We want to reach the step number 4 and we are only allowed to take either 1 step before reaching the 4, or we can take 2 steps before reaching the 4. Now if we want to take only 1 step before reaching the 4, then we must be at step number 3 to do that. Similarly, if we want to take 2 steps and jump from the previous step to reach the 4, then we must be at step number 2. From here, we are getting very close to the final solution. we want to reach the step number 4, we are only allowed to take 1 or 2 steps at a time. We are not sure about number of ways of reaching 4, but we are sure about the fact that all the ways in which 4 can be reached will have 1 as the last step or the 2 as the last step. So if we can find the number of ways in which 1 is a last step and number of ways in which 2 is a last step, then we can simply add these two numbers together and get the number of ways in which we can reach the step number 4. Now how do we find number of ways in which 1 will be the last step and how many ways in which 2 will be the last step? And this answer will be given by step number 3 and step number 2. Step number 3 and step number 2 will take care of finding how many ways in which those two steps can be reached, and using those two answers we can find the answer for number of ways in which the step number 4 can be reached. If we are to put this in a mathematical function, we can say that f of n is a function that gives number of ways in which nth step can be reached, and for that we will need answer to f of n minus 1, because from all those ways we can take one extra step and reach the nth step, plus f of n minus 2, because from that step we can take 2 steps and directly jump to the nth step. And as a base cases to this function, we know that when n is equal to 1, the number of ways are 1. So we can say f of n equal to 1 when n equal to 1, and similarly f of n equal to 2 when n equal to 2. Now we can easily implement this in our code. If we implement it as is, then this would be a top-down approach of dynamic programming. On the other hand, we can also think about the bottom-up solution. We already know that when n is equal to 1, the answer is going to be 1. When n is equal to 2, the answer is going to be 2. And now when n is equal to 3, we will add f of n minus 1, that is f of 2 plus f of 1, that is going to be 2 plus 1, that is 3. So f of 3 will be 3. And if we want to find f of 4, then in that case f of 4 will be addition of f of 3 plus f of 2, which is nothing but 3 plus 2, it would be 5. And similarly, if you want to find f of 5 will be f of 4 plus f of 3, and it would be 5 plus 3, that is 8. Now before moving to the coding part, let's also discuss why this problem is a dynamic programming problem. It's just a function, and how does dynamic programming come into picture? In the previous video, we discussed two properties of dynamic programming problems. One is optimal substructure. Optimal substructure property suggests that optimal solution to a problem can be found out by optimal solution to the smaller subproblems. And in this case, we can see that when finding the answer to f of n, we used f of n minus 1, which is certainly a smaller problem compared to f of n, and also we used f of n minus 2, which is again a smaller subproblem than f of n. So the optimal solution to f of n minus 1 and f of n minus 2 led to the optimal solution of f of n, and hence this problem holds optimal substructure property. Now similarly, let's also discuss overlapping subproblems. Let's say we want to find number of ways in which 5th step can be reached. For that, we will need the answer to number of ways in which 4th step can be reached and 3rd step can be reached, that is f of n minus 1 and f of n minus 2. But for finding number of ways in which 4th step can be reached, we need the answer to f of n minus 1. In that case, it would be 3, and n minus 2 would be 2. And here we can clearly see the overlap. F of 3 will get calculated multiple times. And this is what the overlap is. But from here we can say that this problem also holds overlapping subproblem property. If we expand this further, we can see f of 3 needs f of 2 and f of 1. Similarly, this f of 3 will need f of 2 and f of 1. And hence, entire subtrees are going to get overlapped. Now let's move on to the coding part. As this problem is fairly small in terms of code size, we will implement it in both ways, bottom up as well as top down. For the top down, we have already discussed a template in the previous video. We will continue to use that, and we will see how easy it is to also implement it in the bottom up approach. Let's move on to the coding part. As we know, when n is equal to 1 or n is equal to 2, we can simply return it from here. So we can just check that condition first. So if n less than or equal to 2, return n. Otherwise, we can say that return climb stairs of n minus 1 plus climb stairs of n minus 2. However, as we discussed, there are going to be overlapping subproblems and we want to be efficient about it. So we will calculate the result and store it in a storage. All this is already discussed in the previous video. So if you haven't watched that video, I would strongly encourage you to watch that so that nothing is missed in between. Alright, so we will use the storage. Let's say we will use a hash map. So unordered map of int. Now key will be the n that we are trying to solve the problem for, and another int would be the answer that it will store. Let's call it storage, and we will always check the storage whether it has the answer for the current n. Now in the beginning of the climbing stairs, we checked whether n is less than or equal to 2. In that case, we can simply return n. If that is not the case, we can consult the storage. If storage dot find n, if storage already has the answer, then we can simply return the answer that is readily available in the storage. So if answer storage dot find is not end, then in that case the answer exists in the storage, so we can say storage of n. And if it does not exist, then we are going to calculate the answer, and we will store this answer in the storage for the future references. So we can say storage of n is equal to climb stairs of n minus 1 plus n minus 2, and then return storage of n. If you want to simplify this further, we can say storage.find. If we don't find it in the storage, then compute it, and at the end return it from the storage. And if you want to even reduce the code size further, we can put answers for n equal to 1 and 2 in the storage at the beginning, and then we don't even need this check in the beginning. So in the beginning, we can store in the storage key 1 and answer 1. Similarly, key 2, answer 2. We can try and run this code. It works as expected for the given test case, but it's always a good idea to add a few more test cases. So for we already have the answer to n equal to 3, n equal to 4, and n equal to 5. So let's test with that. Great. For n equal to 2, the answer is 2 in the output as well as in the expectations. And for 3, 4, 5, we already saw that the answers were 3, 5, 8, and that's what we are returning. So let's go ahead and submit this solution. Alright, it works. Now this was the top-down approach that we implemented. Let's also implement this in the bottom-up approach. And you will find that both are fairly close to each other, and none of these are difficult as such. For the bottom-up approach, we will simply store the answers in a vector, that is an array, where ith index will hold the answer for number of ways in which ith step can be reached. So let's say vector of integers, and we can call it storage again. We already know that the number of ways in which 0th step can be reached is 1, that is not do anything, so we'll put 1. Number of ways in which first step can be reached is 1, that is go from 0 to 1, and number of ways in which second step can be reached is 2, because we can go from 0 to 1 and 1 to 2, or directly from 0 to 2. So now that we have initial values in our storage, let's run a loop for reaching the nth step. So for int I equal to 3, I less than or equal to n, I plus plus. In the storage, we can store storage.push underscore back. So append at the end, sorry, typo here. Append at the end, the answer for I equal to 3 will be addition of answer for I equal to 2 plus I equal to 1. So that is storage of I minus 1 plus storage of I minus 2. And at the end, because we want to return the answer for nth step, we can simply return storage of n. And we can again try and run this code, and it again passes the test cases that we had provided. If you observe carefully, as you can see, we only care about the previous two values, and we don't need all values in that storage. There is certainly a scope of optimization here in terms of space complexity. I will leave it up to you whether you want to optimize it further or not. For now, we can just submit this code and see if it works. Great. So let's quickly discuss the time complexity and space complexity of this solution. Let's start with the time complexity. Declaring the storage, it would be a near constant time, so we can just say constant time. This loop is going to run in the proportion of n, let's say n times. Precisely, it's going to be n minus 2 times, but anyways, in the time complexity analysis, we ignore the constant, so we can just say this loop is going to run n times, and this insertion at the end of the array is also going to be a constant time. So we can say that n times we are going to run a constant time operation. So the time complexity of this for loop is going to be big O n, and plus we have this constant time operation at the beginning. So overall time complexity of this solution is going to be big O n. Similarly, for the space complexity, at most there are going to be n numbers in this storage, and hence the space complexity is going to be big O n as well. Now, some of you might think about how to find the time complexity of the previous solution, which was a top-down solution and it was a recursive solution. In some of my other video, I have mentioned that I'm going to make a dedicated video to discuss how to find the time complexity of recursive solutions, and hence I'm not going to discuss that here. But in the meanwhile, if you're really curious about it, I have written a fairly easy to understand blog post about it, and you can find that on my website. I'll post the link to that blog post in the description below, so do check that out. I hope that you like this interesting problem that is not so difficult to understand and write the code of, and still introduces you to the dynamic programming. If you enjoyed learning something new today, give this video a thumbs up and share it. Post any questions in the comments below so either I or someone from the community can respond. I would also love to hear any suggestions and feedback that you may have. Don't forget to subscribe to Interview Recipes. See you next time and bye for now.